Miriam Garcia is going to introduce Aida. So again, thank you very much, Aida, for joining us, and everybody for also being here in this let's see what happened. Hope you enjoy.
So good afternoon. It is my great pleasure to introduce Aida Wofford. I'm sure most of you know her. I don't know, I could be telling you about her awards and grants and many successful proposals. But what I really like about, well, I like many things about Aida, but I think it's very interesting that she is kind of halfway between massive stars, star-forming galaxies, and the interstellar medium. So I think her work is a very nice bridge between different communities, and I'm sure her talk is going to be very interesting. So just very briefly to say, she's currently a tenured professor at Universidad Nacional Autónoma de Mexico, and she had a very outstanding postdoc, I would say, at Hubble Space Telescope and the Institute of Astrophysics of Paris. And I think those provided her with a very interesting background. So without any further ado, I would give you Aida. And again, Aida, I would also like to thank you for giving the talk at this very early time in the morning. And I hope you all enjoy.
Hey, so thank you so much for the invitation and for being here. So what you see here on the left is a starburst galaxy NGC 3125. And it's nearby. It's located at about 15 megaparsec. And overlaid on the galaxy is a circle that represents the aperture of a spectrograph. And I will show you spectra from that spectrograph later. It spans about 140 parsecs across. And then what you see on the right is galaxy 131717, a high star-forming galaxy that's located at a redshift of 3 in the Chandra Deep Field South. And we think that we have found very massive stars in these two galaxies. And during my talk, I will present evidence for this. And I will also talk about how well current population synthesis models that account for these stars fit the observations of these two galaxies, in particular the rest frame UV. So I will present results mainly from a paper that was submitted in early March. We received the referee report. So if you're in the audience, thank you very much for the very useful comments. This work wouldn't have been possible without the help from two wonderful graduate students, Andres Sixtos and Thomas Stanton, marked in red there. Andres, and of course other collaborators that are also listed. Andres will be in the job market starting in this summer. So let me start by introducing the connection between massive stars, starburst galaxies, and cosmic noon. So I expect this audience, of course, to know what a massive star is, but what is a starburst galaxy? So these galaxies have exceptionally high rates of star formation compared to the long-term average of the galaxy or other galaxies. So the Milky Way, for instance, is not a starburst galaxy. If we let SFR be the star formation rate of the Milky Way is something like 3 solar masses per year, whereas that of a starburst galaxy can be 100 solar masses per year or more. So these galaxies are powered by populations of massive stars. And the first reason why they're important is because locally they're responsible for about 20% of star formation in galaxies. And you see two examples here, the antennae and the galaxy I presented in my first slide. So what is cosmic noon? So I'm illustrating what it is in this cartoon plot that shows the rate of star formation on the y-axis versus time on the x-axis. And the present time is on the right. And the black curve shows how the rate of star formation increases with time until it reaches a peak at a time called cosmic noon. And this is between redshifts of 2 and 3. And then it increases exponentially in the cosmic afternoon. So nearby starburst galaxies are also important because they are the most obvious counterparts of normal star-forming galaxies at high redshifts, in particular those at cosmic noon between redshifts 2 and 3. And the epoch of cosmic noon is ideal for studying the mechanisms of star formation, because this is when galaxies form about half of their current stellar mass content, and black holes as well. Okay, so now, of course, there are many properties of galaxies that one can study, but in this talk, I am going to focus on galaxies that have broad helium-2 emission, some in the nearby universe and some in the distant universe. So let me say a few things about broad helium-2 emission from star-forming galaxies. So in the optical and UV, the strongest helium-2 lines are 4686 in the optical, 1640 in the UV. In nebulae with helium++, the lines from helium, the helium++ ions recombine with electrons and form the helium-2 lines. Okay, there are other processes that also produce this line, but when you have a nebula that has a significant fraction of helium++, you will see helium-2 from recombination mostly. Other processes are fluorescence and collisionally excited. The levels can be collisionally excited and then emit as they come back to lower energies. Okay, so ionizing helium+ requires photons energies greater than 54.4 electron volts or wavelengths shorter than 228 angstroms. And main sources that produce these photons in galaxies are some massive stars, accretion disks of black holes, which can be stellar, or also the central black holes of galaxies, and fast radiative shocks, for example, from supernova explosions. Now, broad, that means with a full width half max of 1,000 kilometers per second, helium-2 emission at 1640 angstroms is the strongest stellar feature in the stacked UV spectrum of Lyman break galaxies located at cosmic noon. And this is reported in Shapley et al. 2003. So it's the strongest stellar line. And what are Lyman break galaxies? These are star-forming galaxies at high redshift that are selected using the differing appearance of the galaxy in several imaging filters due to the position of the Lyman limit at 912 angstroms. And so on the right, you see a spectrum of a Lyman break galaxy that spans from the FUV to the near IR. And the Lyman limit or Lyman break is indicated by the vertical dashed red line. And in the bottom panels, you see how this galaxy looks in different filters. And you see that in the far ultraviolet, at shorter wavelengths than the Lyman break, the galaxy disappears because the galaxy is very faint there. And this is how they are selected. Okay, so for these galaxies, when you combine their spectra, the broad helium-2 line is the strongest stellar line. And what I show now is a stack of 811 galaxies that is presented in Shapley et al. 2003, where they combine 811 spectra. That's what a stack is. And I have marked in red, for those who see red, sorry, the helium-2 1640 line. This is a rest-frame UV spectrum. The very strong line that you see here is Lyman alpha. And you also see other interstellar medium lines and fine structure emission lines, etc. But as you can see, the helium-2 line is broad and strong. Okay, so you may wonder, okay, I combined a whole bunch of spectra, and how do the uncertainties influence the width of the helium-2 line? Well, very recently, there was a very deep 20-hour VLT observation of a UV bright non-lens star-forming galaxy. And that's the galaxy I showed you in my first slide. That galaxy is located at a redshift of about 3, and it clearly shows a broad helium-2 line, which you see in the figure there. The spectra is in black, and in red there's a model that fits the continuum plus a Gaussian at the location of the helium-2 line. And then you see on the right panel the feet in velocity space of the helium-2 line. And this is how we know it's broad, and it has a full width half max of about 920 kilometers per second. This galaxy has mass in stars in units of solar mass of log m Remsen of 9.68. The observation is part of the Deep Public Isospectroscopic Survey with VMOS on the VLT. It's part of the Vandals survey that's presented in McClure et al. And Garilli et al. And it clearly shows then the existence of broad helium-2 in a single object from a distant redshift 3 galaxy. And this object will be presented in detail in Stanton et al. In prep. Okay, now can models reproduce the broad helium-2 emission from Lyman break galaxies? So when Shapley et al. Published their stack spectrum, the helium-2 line was the only discrepant stellar line when comparing this spectrum to model spectra of stellar populations available at the time in 2003. And in particular, those generated with the widely used stellar population synthesis package starburst 99 by Leiter et al. And the models are for single non-rotating stars with an upper mass limit of the stellar initial mass function of 100 solar masses. And this discrepancy between the helium-2 of the stack of high redshift galaxies and the models is reported in Chandler et al. 2004. So let me move on now to galaxies at low redshift. Do we see such profiles from populations of massive stars? So the answer is yes, and some nearby starbursts actually have really strong lines with equivalent widths greater than 2 angstroms. And throughout this talk, positive equivalent widths will be emission. This is what extragalactic astronomers use. So examples, notable examples, are the galaxy that I will be mainly talking about later, and in particular cluster A1 in NGC 3125, and cluster 5 in NGC 5253, and then there's a cluster also in galaxy 1 Zwicky 40, SB 179. And until very recently, such lines, I mean, the broad helium-2 lines were really challenging to model. Before I show you comparisons of models with observations of nearby objects, let me show you just an example, a nearby example. So this is starburst galaxy 5253. It's at about 3 to 4 megaparsecs, and you see cluster 5 indicated there in yellow. And on the top right, I show the optical spectrum with the helium-2 line marked in red. And on the bottom, you see the UV spectrum with the broad line marked in red as well. Okay. So what causes extreme broad helium-2 emission from star-forming regions? So in integrated spectra of massive star populations, broad helium-2 emission suggests stellar winds as the formation mechanism. Conditions for detectable stellar emission are that the stars must be hot to doubly ionize helium-2. Mass loss rates must be high to produce dense winds. And having an overabundance of helium helps, but is not necessary. And because classical Wolf-Rayet stars, which are helium burning and have a deficiency of helium in their atmospheres, meet all these 3 conditions, the presence of broad helium-2 is generally thought to indicate the presence of Wolf-Rayet stars. Now, what about very massive stars? So these are stars that are defined to have masses of greater than 100 times the mass of the sun, as defined in Vink et al. 2015. And this is above the standard upper mass limit of the IMF that is used in population synthesis models. And so these stars can produce Wofford-like features even during core helium burning, independent of helium enrichment. And in very massive stars, the reason for the increased equivalent width of the helium-2 4686 stellar wind line is almost certainly the proximity to the Eddington limit. And this was shown in figure 10 of Vink et al. 2011, which I show on the right, where the y-axis gives the normalized flux and the x-axis gives the wavelength. And the curves that you see are the helium-2 4686 line predictions for different gamma factors. So gamma is equal to 1 when the radiation forces balance the force of gravity. And you see that for greater gamma factors, the equivalent width of helium-2 is larger. So there is evidence for the existence of these stars in the R136 cluster of the LMC, and this is being reported in Crowther et al. 2010 and 2016. On the left, I show the HR diagram of the most massive stars in R136 from Crowther et al. And you can see the symbols are the observations, and you see 3 stars, for instance, above the track of 200 solar masses there, which are very massive stars. And then the positions of these stars in the cluster are shown in this figure by Brands et al. 2022. So the color bar on the top gives the mass of the star, and in red, if you can see red, there are those are the stars with greater than 100 solar masses. In this figure, the parallel lines correspond to HST's long slits. Okay, so very massive stars are important in studies of helium-2 emission because they dominate when they are found in a population of stars. They dominate the helium-2, the broad helium-2 emission, and this is shown in this figure of Crowther et al. 2016, where you see the rest-frame UV spectra of stars in R136. The top black curve is the spectrum of all of the stars that were observed. And the bottom spectrum, the dotted line curve, is just the 7 very massive stars in R136. And you see that the helium-2 line comes primarily from these 7 stars. If you go to the second curve from the bottom, that's the non-very massive stars. So there's 63 of those stars, and you see that there's no broad helium-2 emission. Okay, now let me move on to one of the galaxies I want to tell you about, and in particular a cluster within this galaxy, which is A1 in NGC 3125. I already said that this is a starburst galaxy that's nearby. It has an ionized gas oxygen abundance of 12 plus log O2H of 8.3, as determined by Hatfield and Crowther 2006. And it's consistent with abundances in the Large Magellanic Cloud obtained via collisionally excited lines by various authors. And it's characteristic of some star-forming galaxies at cosmic noon. That means at redshifts 2 to 3. It hosts a cluster with a young age, 2.2 million years, and a high mass, about 2 times 10 to the 5 solar masses, which is A1 and is considered to be a superstar cluster. And so you see it there, it's the white brightest dot indicated by the arrow. And the parallel lines here are a long slit that was used to observe this in the far ultraviolet. So what you see here on the left is the STIS G140L 2D spectrum of the galaxy obtained by Klaus Lederer a few years ago. And I'm showing this because you can clearly see which are the bright UV clusters in the galaxy. And you can even see the helium-2 emission of A1, which is indicated there on the left. By the way, the spectral resolution of the STIS spectra is 164 kilometers per second. The parallel lines are the 2 arcsecond wide STIS slit, and there are other UV bright clusters as well, but we're going to focus on A1. Now, as you can see, you cannot see individual stars in this A1 cluster. So how can you study the massive star content of this cluster? So for that, you use population synthesis models, which are a main tool to study unresolved stellar populations. These combine evolutionary models, which some of which account for rotation or closed binary evolution and the latest developments of wind theory, with empirical or theoretical spectra. What they predict, or one of the most important predictions of these models, are the spectral and photometric properties of stellar populations. And the simplest stellar population model that you can generate is what's called a simple stellar population, where the stars are all appear in a single burst and they're coeval. Okay, and so I tried to illustrate what these models are on the right. Of course, you need to provide a initial distribution in mass of the stars in order to generate your SSP, simple stellar population model. Okay, in 2014, we showed that if you use a standard stellar initial mass function, where the upper mass limit is 100 solar masses and where the power law exponent for the massive stars is alpha of 2.3, then you cannot reproduce the helium-2 emission of A1. And so here the model is in red and the STIS observation is in black. And as you can see, the helium-2 line is not reproduced. However, very recently, we have finally been able to reproduce this line. And so Martins and Palacios were the first to apply population synthesis models to young clusters, accounting for enhanced mass loss from very massive stars close to the Eddington limit. And it seems that this is what does the trick, so the being close to the Eddington limit. So using simple stellar populations model with BPAS that ignore, in this case, closed binarity, in combination with very massive stars close to the Eddington limit, sorry, there's a typo, this enabled them to reproduce the helium-2 line. And you can see the model, which is for a population of 2 million years. So they use BPAS for stars from 0.1 to 100 solar masses, and then they add very massive stars close to the Eddington limit to that. They are able to reproduce the helium-2 1640 line. Now, this is not a model that's tailored to A1 like the one that I am going to show. So there are some problems, but their goal was to reproduce the helium-2 line and they succeeded. Okay, so we use higher spectral resolution observations of A1 than the STIS observations that I have shown you so far. And they were obtained with gratings G130M and G160M. And a main reason for using G160M, which is the one that catches the helium-2 1640 line, was to check for contamination of the helium-2, of the broad profile with narrow nebular emission, because there's a giant H2 region around this cluster. And so with STIS, which has a spectral resolution of about 200 kilometers per second, you cannot see if there's you cannot clearly see if there's narrow emission, which you expect to have a width of about 100 kilometers per second. So we use this data, and then we undertook a tailored analysis of the observation of A1 using independent population synthesis models, so different than what Martins and Palacios used. And I forgot to say that the spectra are in the rest frame UV. Okay, so before I go into whether the spectrum is contaminated with nebular emission, let me talk about contamination of the nitrogen 5 1240 profile with Lyman alpha absorptions from the Milky Way and the galaxy itself. So removing the Lyman alpha absorption profiles is a critical step for finding an accurate model fit to the observations, because these lines severely contaminate the nitrogen 4 profile. And so we corrected for Lyman alpha absorption by adopting a similar approach as that described in Hernandez et al. And Ciresi et al. And this correction was not done in Martins and Palacios, and this is why probably their nitrogen 5 profile doesn't fit. So what we do first is that we fit the continuum. So what you see here is the spectra, the cost spectra that we obtain. And so we fit the continuum, and you can see here that there's a broad absorption. That's the result of absorption of Lyman alpha photons in the Milky Way and also in the galaxy NGC 3125. And then we normalize the spectrum by dividing the original spectrum by the fit to the continuum. And after we've done that, we fit void profiles to the two absorptions, the Milky Way absorption and the galaxy absorption. And this is done here. And then what we do is that we divide the normalized cost spectrum by the best Lyman alpha fit to remove the contaminating profile. So this was the original here in blue, and the corrected one is the black one. Okay, and you can see that it makes a difference for the nitrogen 5 profile. So we did that before comparing to our models. Also, we checked, like I said, for the presence of nebular emission, because we don't want to fit a stellar model to a model that contains nebular emission. So you see here the broad helium-2 profile of cluster A1 in black in the top panel. And we fitted a single Gaussian to this profile, and it provides a very decent fit. And what we find is that we don't need to add to these a narrow fit to that would correspond to the nebular emission. And from this fit, we find that the profile has a full width half max of 1131 kilometers per second, an equivalent width of almost 5 angstroms, so it's extremely strong. And the other thing we find is that this profile is slightly redshifted relative to the lines we use for the rest frame of the galaxy, which are ISM absorption lines. And it's redshifted by 121 kilometers per second, approximately. The bottom panel here shows the residuals. Okay, so in these slides, I show that an equivalent width of 5 is uncommon in the nearby universe. And so what this plot shows is, so first the color bar is, okay, so let me start again. What I show here is the comparison of observations of the equivalent width of helium-2 1640 versus the equivalent width of the absorption component of the carbon-4 1550 profile versus models. So the models are the circles and the color circles, which are coded by age, and the age goes from 1 million years at the bottom to 7 million years at the top. And the black cross is cluster A1, and the gray crosses here are other galaxies that have been observed in the UV with Hubble, and which have good measurements of broad helium-2. And so you see that our galaxy is among the strongest emitters. The models here are for simple stellar populations that include very massive stars near the Eddington limit with a metallicity that's close to the one of this galaxy. Some of these galaxies have very different metallicities, so that can be a bit misleading. This is just to show that the equivalent width of helium-2 of this galaxy is very strong. Okay, now we have this beautiful data. So do we have models with close that account for close binarity that can fit this data? So like most of you know, there's evidence that most massive stars are in close binary systems where the stars exchange mass and rotate, which affects the revolution relative to models where massive stars evolve as single non-rotating stars. And this is shown in Sanael and papers after that. And so a code that is very well known that includes closed binary evolution is BPAS by Eldridge et al. 2017 and binary et al. 2022. And so can we use these models to reproduce the data? So let me show you predictions of the helium-2 1640 profile by BPAS binary. So what you see in this panel is the normalized luminosity for a cluster of 10 to the 6 solar masses versus wavelength. And the different curves are models, simple stellar population models with very massive stars at different ages. And so this pistachio color one is the one that produces the strongest helium-2 1640 line, and that's at 6.3 million years. And so if I overlay the model corresponding to that profile to the observation, which is in black here, you see that the model with binaries fails to reproduce the helium-2 line. And that's the one with the strongest helium-2 predicted by BPAS. So why is that? So that's because in the BPAS binary models, there's a lack of consideration of higher mass close to the Eddington limit. Okay, so as far as I know, currently we don't have a population synthesis with binaries that account for very massive stars close to the Eddington limit. And so that's why these models won't be able to reproduce the broad, strong helium-2 line. Okay, so the models we use are Charlois-Brusois models that account for very massive stars near the Eddington limit. They're based on parsec stellar evolution models. They ignore rotation and close binarity. And the syntectic atmospheric models that they use involve velocity, WM basic, and power. And so here's the comparison of the COS observations and the Charlois-Brusois models. And the model is shown in blue. The model that best fits is for a metallicity of 0.008, an age of 2.2 million years, and a cluster mass of 1.9 times 10 to the 5 solar masses. And the model reproduces fairly well the helium-2 profile, which is in the bottom panel, but also the carbon-3, 1175, the nitrogen-5 profile that's been corrected for Lyman alpha absorption, and the carbon-4, it's a bit strong in emission. So overall, we think that this shows the great improvement of models over the past decade. Now, this is a very young age, 2.2 million years. So at this age, very massive stars are present. But like I mentioned before, classical Wofford stars have features that are also present in this spectrum. So can helium-burning Wofford stars reproduce the spectrum of A1? And the answer is no, because we see strong oxygen-5 absorption, which is marked here, in the spectrum of A1, which is a sign of a very young age of less than 3 million years, and classical Wofford stars appear after this age. So this is how we can rule out older models. So these are predictions of the oxygen-5 1371 profile at the metallicity of the galaxy. And so the panels show different ranges in age So the top panel shows from 1 million year to 1.9, then 2 to 2.9, and 3 to 3.9. And so you can see that the profile, the absorption part of the P Cygni is strong at young ages that are younger than 3 million years. Okay, but this is when the Wolf-Rayet stars are. Okay, now this plot on the left shows the number of different types of evolved stars, but also all stars. So we have the classical Wolf-Rayet stars with different colors, and then we have the total number of classical Wolf-Rayets in purple here. And then we have very massive stars in brown. We have all stars, main sequence and non-main sequence, with the dotted pink line. And this is versus age versus time from 1 to, I think, 7 million years. And you can see that at 2.2 million years in these models, there are very massive star presence. So that's the brown curve. But I'm also showing this plot because this plot also shows the rate of ionizing helium-2 photons as the gray dashed line. And you can read the rate here on the right axis. And something strange in these Charlotte and Broussard models, but this is also true in starburst 99 models, is that when the Wolf-Rayet stars appear, the rate of helium-2 ionizing photons increases. And this was first noted in a paper by Sixtos et al. 2023, which is called Looking for Nebular Helium-2 Emissions Out of Multiple Star System HD 5980. And so in this paper, this was noted, and the case for starburst 99 is also shown. So this is a problem because, so according to the experts, and in this case, our expert was Andrea Sander, you shouldn't expect that the winds of classical Wolf-Rayet stars or even very massive stars are transparent to helium-2 ionizing photons. Okay, so this increase here probably means that these population synthesis models have a tendency of selecting atmosphere models for Wolf-Rayet stars that are transparent to these photons. So that's something that probably needs to be improved in future models. Okay, so finally, let me talk about this faraway galaxy at redshift almost 3 in the Chandra Deep Field South. So I'm showing here the observation in black. Remember, this is a 20-hour observation on the VLT. The galaxy has a strong equivalent width of helium-2, broad helium-2. The width is about 920 kilometers per second. The equivalent width is 2.5 angstroms. It also shows tentative evidence for oxygen 5. Now, there are no other broad emission lines in this galaxy, and this is how we know that this is unlikely to be an active galactic nucleus powering the helium-2 emission. And only less than 2% of sources at cosmic noon have broad helium-2 profiles. Okay, so this is a rare object, and this is reported in Saxena et al. 2020. The blue line here is the error array offset. Okay, now I'm going to show you now a preliminary model with very massive stars. So this is a simple stellar population Charlotte and Broussard model with very massive stars close to the Eggington limit. And with a model of 2.3 million years, we can reproduce or approach the strength of the helium-2 profile. So based on the fact that these objects are rare at high redshift, objects with strengths of the helium-2 profile greater than 2 angstroms are rare, less than 2%. Based on the fact that there's tentative evidence of oxygen 5, then we suggest that there might be very massive stars in this object. This object will be studied in great detail in a paper by Santon et al. In PrEP. They also have optical spectra for this object, so look forward to that paper. And so here's my summary. Superstar cluster A1 in starburst galaxy NGC 3125 has one of the strongest broad helium-2 emission line ever observed in a nearby starburst galaxy. The profile is redshifted by 121 kilometers per second. I forgot to say why we think that is. Well, we think because it is dominated by very massive stars, and in very massive stars, this profile is in a P Cygni profile with a redshifted emission. Of course, we're looking at a population, so you don't see the P Cygni profile. I compared the COS observations of A1 to the latest Shaogan-Brusois population synthesis models with very massive stars near the Eddington limit. A single non-rotating Shaogan-Brusois model with an age of 2.2 million years provides a very reasonable fit to many UV diagnostic lines and the helium-2 stellar wind feature. And then I suggest that there are very massive stars present in this distant object that's a highly star-forming low metallicity galaxy. And so I confirm that it is important to account for very massive stars in population synthesis models, very massive stars near the Eddington limit. And now just a lesson for I guess, students or early career people here. What's the importance of broad helium-2 emission for unresolved stellar populations? Well, it is an indicator of youth. So if you see it in a spectrum, that means that your population is quite young. And then if you see it in combination, say, with absorption of oxygen-1 and weak silicon-4 1400 emission, that means that there's a population of less than 3 million years. Which has very massive stars. And if you don't see this strong absorption of oxygen-5, then your population is young, but not so young. It may be 3 to 4 million years and have classical helium-burning Wolf-Rayet stars. And so with that, I conclude. I was told, though, that I could advertise a little bit my institute. So here's my advertising slide. So this is the Institute of Astronomy in Ensenada, Baja California, Mexico, where I work. So you see, we have a very nice building with a lovely terrace where we read papers and have great discussions. We do a lot of outreach. And here you can see the terrace during the partial eclipse in 2017. And here talking to some kids, teaching them how to find constellations. And then in the bottom row, you see pictures taken from our national observatory, which is 3 hours south. I picked this one because it has some really nice lightning showing. And of course, you probably don't know where this is. So it is super far away from Mexico City. You need to drive 47 hours across Mexico to get to the observatory. There's 3,400 kilometers from Mexico City. And so we're up here near the border with the US. And the observatory is here in the middle of the national park in the Baja Peninsula. And so we offer Masters of Science in Astrophysics and Instrumentation, PhDs. We have postdoc offers every 6 months. So look for those in the AAS job register. And we will be opening 2 faculty positions next year. So thank you very much.
Thank you, Aida. Very, very nice talk. And I think it very much follows the spirit of, sorry, I just got a message from another source and I was distracted. Yeah, I was thanking you for the talk because it really, really follows the spirit of what we wanted. It's very specific results with detailed explanation, but also the broad context. So I thank you very much for the effort. So for the questions, I think we've had a couple of them in the chat during the talks. I think I'm going to begin with them. If they are still online, please, Arpita Roy, can you make your question aloud, please?
Yeah, hi, Aida. It was wonderful talk. Actually, yeah, no, towards the end, I saw that you are talking about probably the metallicity of those galaxies, which are, I think, Z 0.008, which is like less than 1/10 of solar metallicity, right? So all your galaxies that you are talking about at Z equal to, like at redshift of 3, all the stacked galaxies, they have typical metallicities, I guess, less than 1/10 of solar metallicity. Am I right, or am I missing something?
So now we have individual spectra, right? And so there's some variation, but they are metal poor. Yeah. And a lot of them have metallicities near the LMC, SMC. And they go, and I know that people have fitted models of 1/10 solar metallicity, where solar is 0.14. Okay. And they're consistent with metallicity of 1/10 at those distances.
So all your data as well as your models, they are at more than 1/10 of solar metallicity, right?
Yeah, if you use for solar 0.014, which is Asplund 2000.
Yeah, either 0.14 or 0.12, depending on whether you are looking at the bulk or
right.
Yeah. So anyway, and the other query that I had was like, when you are talking about, so what I got the gist is that there are 3 ways that you can produce these helium-2, broad helium-2 emissions. One is you have very massive stars, another one is binarity, and the third one is probably high mass loss. Somehow you incorporate high mass loss. But are there any models that show that you have single massive stars, but they are fast rotators and they're producing this broad helium-2?
So the Starburst 99 group is in the process of updating their code with rotating stars. So right now I don't have the answer, but I will have it very soon. I'm part of the collaboration. I can tell you that they are using the Geneva rotating tracks. And they're calculating atmosphere models to go with that now. And so we will see what the effect of rotation is, if you can wait a few months.
Okay, and probably the last query that I have is like, okay, you are talking about these parsec models and probably Salo and CNB models that for your single massive stars, but did you look into how they're calculating the effective temperature? Is it just from the stellar interior calculation, or after the interior is done, you have this extended atmosphere because of the ultraviolet mass loss, and etc., and then you have this opacity corrected effective temperature calculation? What is going into the population synthesis code for calculating the ionizing photon budgets? How exactly effective has been calculated, and that goes into the population synthesis code? Because what I recently figured out in the Geneva code, there are 2 effective temperatures. One is what is directly coming from the stellar interior modeling. Another one is you incorporate this extended atmosphere and then the opacity corrected effective temperature. And depending on which one you are using, you will get huge difference in the helium-2 ionizing photon budgets. Actually, if you look at the cumulative one, you can get 5,000% different helium.
Okay. So the answer is I don't know, but I'm going to direct your question to Stéphane Charlot, who's the person who does that part of the models. So if you can email me your question, and I will direct the question to Stéphane.
Sure. Thanks, Aida.
Okay.
So I'm going to have the chairperson power to say that there's another thing we've been discussing recently, and that there's another important point, and is how far your stellar atmosphere model, how far the calculations for the stellar atmosphere model extend. It's not the same stopping at 50 stellar radii that 200 stellar radii. But yeah, we can continue this discussion via email. So I think next, I'm not positive. We also had a question from Zinab Korami. Please, can you make the question?
So I think was not able to use the microphone, so maybe we can ask. It was asking, shouldn't helium lines be asymmetry if they've been reshifted?
Shouldn't helium-2 be?
If the helium line should be asymmetric if they have been redshifted. Sorry.
So what we think we're seeing, the emission is redshifted because it's the combination of the emission component of the P Cygni profiles of the very massive stars. And then I guess the bluest part of the profile is probably filled in by the underlying stellar population, is how I interpret what we're seeing. So yes, it like if you were just looking at the very massive stars, it would have a P Cygni profile and it would be asymmetric. But we're seeing an entire population. I don't know if that answers the question. If not, email me and I will try to answer better.
Okay, so next in line, I think it was Sally. Sally, please unmute yourself and make the question.
Actually, the order is Artemio, Yo, me, and Miguel.
Well, anyway, you go ahead. Then I will go to Artemio. Okay, Artemio, please.
Okay, so thanks, Aida. Very nice talk. And probably you said it, but I missed the point. What's the IMF that you are using in the calculations with the Brussels models? And if this is a standard or different, has it an impact on the results?
It's a Chabrier IMF, which it is similar to Salpeter for the massive star part of the function, and it's not standard in the sense that it includes, well, the upper mass limit is 300 solar masses. And yes, if you don't include the 300 solar mass stars, there's a difference. You cannot reproduce the strength of the helium-2 profile of this particular cluster A1, which is one of the strongest helium-2 lines ever observed in the nearby universe.
Yeah, that's clear. The question is more that if you use something like the IMF derived by Fabian Schneider in Certitoradus, for example, in Ars 136, then you produce more massive stars. So you will have, not for the most massive, which reproduce your helium-2 line, but you will have more stars of high masses, not of the highest mass, of the highest one. And whether this makes a difference in the rest of the spectrum. I understand that helium-2 is dominated by the most massive ones.
Okay, I have not tried that IMF, but I can tell you for properties like the total mass in stars of the cluster, it's not gonna make an order of magnitude difference. So the cluster will still be around 10 to the 5 solar masses.
Okay, thanks.
Mm-hmm.
So Sally, are you next now, or is it Joe?
It's Yo.
Okay, Joachim, please.
Yeah, thanks a lot for this very nice overview, and I guess it was also very deductive, so I think it's particularly for the younger people, and your last slide was really perfect. I have just a comment, not a question, to your very often statements that this line is asymmetric, and this has to do with basically that it is in at least the contribution from the massive stars is more P Cygni line, and also to the question whether the high redshift, when you de-redden it, so to say, now with redshift, that it might be this effect. So let me at first say, I think the line is too narrow, that here the redshift really plays a role for the for the asymmetry. And the asymmetry itself is related simply to the fact that these winds or the velocity fields in these winds are not monotonic, but they have a certain velocity dispersion, which is related to all these inhomogeneities which are in the literature. And these kinds of inhomogeneities lead to a velocity dispersion, which makes the total thing a bit, the radiative transfer a bit asymmetric, and then you get this redshifted emission. So that's the simple explanation.
Ah, thank you. Mm-hmm.
Okay, Sally, please go ahead.
Thank you. I was just wondering if you or someone could briefly explain the origin of the oxygen 5-1371 feature and why it shows up in normal stars and not in Wolf-Rayet stars, for example.
Okay, so I'm not an expert in massive stars, but maybe somebody in the audience.
So I guess in this, well, Joachim is the super expert, but I think it has to do with the ionization equilibrium and the surface abundance. You do find all 5 P-Cygni profiles in very early O-type stars. As you go to lower effective temperatures, the line disappears. I'm not so familiar with the spectra of Wolf-Rayet stars. But if you have a nitrogen or a carbon Wolf-Rayet star, I don't know if the matter is that the surface abundance is not so high or the effective temperature is higher and the ionization equilibrium has shifted to higher values. Probably Andreas can comment on that.
Okay, thank you. Andreas, maybe you can email me. Great talk, Aida.
Thank you. Email me too, Andres. I'm interested too.
Okay, so Paul said that the oxygen 5 line actually can have a P-Cygni profile in carbon Wolf-Rayet stars. So yeah, I was. So Paul, can you have the microphone, please?
Yeah, so you certainly can get the oxygen 5 feature, the 1571 feature in WC stars. Yeah, the ionization WC stars have 1370, very strong P-Cygni, very strong emission, but P-Cygni. Whereas what we're seeing here in these models, which are, I guess, basic models, you're looking at the hottest main sequence O stars. So you know, O2 or 3 stars have strong 1371. Strong absorption, weak P-Cygni emission, and I guess it's a combination of at very early ages you have the oxygen 5. At later ages, when you had the OB supergiants come in after maybe 3 or 4 million years, you get strong silicon 4, 1400 P-Cygni lines, and that would then be a similar era to the classical Wolf-Rayets. So if you see strong silicon 4, then you probably expect classical Wolf-Rayet stars to be there, which can contribute to the 1370 line. But if you take a look at individual stars, you would probably struggle more to see the 1370 just because there are relatively few WC stars in a metal poor population or predicted population at the age of 5 million years or so.
Thank you, Paul.
Thanks, Paul.
All right, so I have a last question a last hand raised, but before I give the microphone to Miguel, I wanted to encourage young people to ask questions. So while Miguel asks, please, I hope we get some questions from the younger people. Miguel, please.
Okay, so first, very nice talk. Thanks a lot for that. And I have it's a very nice question, but do you know, well, when you use the atmospheric models, as far as I know, there is no, in the normal atmosphere I usually use, there is no broad alien 2 lines, emission alien 2 lines. So I assume that somewhere in the cracks, you have take or either an atmospheric model from a Wolf-Rayet for a very massive star, or maybe the BM basic model And so my question is, first, there has been new BM-basic models in the atmospheric models in this set of evolutionary synthesis models, or are the older ones that was made by Linda Smith, etc.?
I think there are the older ones.
Okay.
Mhm.
So it's possible, because they doesn't have the world radius fracture, that you take the atmospheric model for a very massive star, taken from the world radius part of your atmospheric model grade. I don't know if you can test it. And my other question is, if you use the same set of atmospheric models, but without massive stars, have you tested if you reproduce this line? Because it's possible, if you have a very hot star, that you go to these kinds of models and you can be able to reproduce also the line.
Okay, so the second part of your question is, if I stop the initial mass function at 100 solar masses,
For
can
example,
I reproduce? I cannot reproduce. I cannot reproduce the helium. That's in the paper, so which will be resubmitted. You will be able to see, because I included models that stop at 100, and I showed that I cannot reproduce the helium-2.
Okay, so you need a really hot stars that are the very massive ones.
Yes.
Okay.
And for the first part of your question, if you could email me that, that would be very useful, and I'll try to address that.
Okay, thank you very much, and very nice start again.
Thank you.
All right, so I see no more questions. So I think it's a good moment to stop here. I thank everybody very much for joining us. At some point, we were 50 participants in the talk, so I think this very first experiment, it's been a success. And I would like to thank you, Aida, again for the effort of giving the talk so early in the morning, and such a very nice talk. So maybe Sergio, maybe Sergio wants to give some closing remarks too.
Yeah, once more, thank you very much, Aida, for accepting our invitation and for being the first one here. And yeah, it has been great to have 50 people. The first